Hey there, calc folks, back here with another video lecture in what my series of lectures looking at what's up with my lights here? Let me turn these down a little bit here. That could be it. In my series of lectures on some integration techniques. In the last video, I looked at integration by parts. What we're moving over into now is the case for trig integrals. We're going to be looking at integration for what is essentially the product and quotients of sine and cosine functions. Right? How do we integrate the product and quotient of sine and cosine functions, folks? Right? We could have just the products of sines with cosines. Right? Or we could consider the quotient of sines with cosines, which forms things like tangents and secants, or with sine over cosine, or forms things like cotangents over cosecants with the cases of cosines over sines. We're going to look at integration strategies for calculating integrals involving these products and quotients of sines and cosines. All right, that is the technique being presented here in this section. Now, I realize I did not break this up, but I'm not going to spend a lot of time on this, folks, so I'm not going to go through that. But and break this up and scroll it down. I'll go ahead and leave it gathered here. But I'll just take note, in this section, we consider the integrals for the cases of integrands involving the trig functions, the products of the trig functions. Right? Which really breaks down to products of sine, cosines, tangents, secants, or cotangents and cosecants. Which, again, I go back to is just the different arrangements for sines and cosines that we could have in product and quotient arrangements. We could have just sines times cosines. We could have sines over cosines, which would produce the cases for tangent and secants. Right? Or we could have cosines over sines, which would produce the cases for the products of cotangent and cosecants. But in all of these situations, it all boils back to a product or quotient of sines and cosines. Where, depending upon the pairing that we see, sine and cosines, tangent and secants, or cotangent and cosecants, we have strategies that are presented in this section. All right. To begin with, we figure just the pairing for sines and cosines, that direct product of a sine of a certain power times a cosine of a particular power. All right. This integration calculation for the sine times a cosine. A sine to a certain power of m times a cosine to the power of n. And depending upon the powers, the behavior of the powers, or really I should say depending upon the even or oddness of the powers, right, and which one is even or odd, we have a different respective strategy. All right. You can take note here. If we consider a sine of m times a cosine of a sine raised to the nth power times a cosine raised to the nth power's integration, right? First thing we would note is if m is odd and positive and n is just a real number, the strategy that we're told to do is to factor a sine of x and to rewrite the remaining even factors of sine in terms of cosine using the sine squared of x equal to 1 minus the cosine squared of x, using that Pythagorean identity. All right? And once done, we can then apply some u substitution, letting u equal cosine of x in this case, which will have the implications that negative du is equal to the sine dx in value. Now that's the case if this power of sine is odd and positive, and n is just any real number. The second case looks at the case, well, what if n is odd and positive and m is any real number? We have a very analogous situation. We're going to isolate a factor of cosine, rewrite the remaining even factors of cosine in terms of sine using the same Pythagorean identity, but solve for cosine squared of x. And then apply some u substitution, letting u equal sine of x, which would imply that du would be equal to the cosine of x dx. This would be our strategy of approach for when n is odd and positive and m is real. Right? If m is odd, we approach strategy 1. If n is odd and positive, we approach it with strategy 2. If they're both even, that's what we see here in strategy 3. If both are even and non-negative integers, we use some half-angle formulas. And we rewrite them into some polynomials involving the terms cosine of 2x and apply the previous strategies in terms of the polynomial forms involving the cosine of 2x. All right. Now, all of these really don't make much sense until we look at a couple of examples. So that's what we see down below here. Here's the first case. We have the integral for the sine cubed of x times the cosine squared of x, all integrated with respect to x. This fits the above form, the integral of the sine raised to the nth power of x times the cosine raised to the nth power of x, where m is 3 and odd and n equals 2 and is real. So following from the first strategy noted above, the integral for the secant cubed of x times the cosine squared of x is going to equal this quantity. If we notice what the above strategy tells us to do, it tells us to isolate a factor of the sine of x, which really means get it all by itself, right, inside of the integrand. All right? That is our first thing here. This is that sine of x. The sine of x is being isolated in that integrand. One of those is being factored from the sine cubed of x. What that leaves then is the sine squared of x times the cosine squared of x. Where the next part of the strategy tells us, rewrite that remaining even factor of sine in terms of cosine using this Pythagorean identity. That sine squared of x is 1 minus cosine squared of x. This sine squared of x seen down here in our calculation is 1 minus cosine squared of x. So if we substitute that in, that would go in right here. And we'd have the sine of x times 1 minus cosine squared of x times cosine squared of x. And then we do a u substitution. What we're told above is to let u equal cosine of x. That does have the implications that the opposite of du would be the sine of x dx. And that lays out the whole purpose of isolating this sine of x dx. You will have a sine of x dx isolated to substitute out with in this u substitution. All right? Letting u equal cosine of x, negative du is going to replace the sine of x dx. This sine of x dx, the sine of x that you isolated, combined with this dx will become negative du. Right? The remaining values in terms of cosine will be replaced, well, the cosines will be replaced with u. So you'll have 1 minus u squared from this factor, and u squared from this factor. So it's 1 minus u squared times u squared. It's opposite. Where if we distribute the opposite u squared, that will become u to the 4th minus u squared, which has a nice antiderivative of 1/5 u to the 5th minus 1/3 u cubed plus our constant of c. Now, this is an integral in terms of u. We want an antiderivative statement in terms of x. That's where we started. And since u equals the cosine of x, we just substitute cosine of x into these statements for u. And we find that the antiderivative of sine cubed of x times the cosine squared of x dx is equal to 1/5, right? Is equal to 1/5 the cosine to the 5th power of x minus 1/3 cosine to the 3rd power of x added to our constant. Coming from this result here, where u is being replaced with the value of the cosine of x. All right. This integrand, this antiderivative, was developed from a little u substitution seen up here, where we let u equal the cosine of x in this integrand. So this portion of our integrand turned into the 1 minus u squared times u squared. The sine of x dx from this integrand is what became the negative du. All right. And this was all a strategy that was given to us from the list above due to the fact that we're looking at a sine times a cosine, where the power of the sine is odd, it's 3, and the power of our cosine here is real, it's 2 in value. All right. That is what strategy 1 is describing up above. All right. Case 2 is very analogous. It's very similar to what we see going on in case 1. Except the cosine and sine change roles in that calculation. That does have one additional difference, and that is in the value of du. Du would actually be equal to the cosine of x dx. Right? Not the opposite of du equal to the sine of x dx. You do have to watch the sign on this du. Not all our cosines and sines swap positions. You also have that little minus du also occurs. All right, but it's very analogous. Whereas case 3 says, well, what happens if they're both even? What do? Well, we're going to apply some half-angle formula. Rewrite it as a polynomial cosine 2x. And apply these ideas above, right? Most likely, probably, well, either of these ideas above. Well, it should be technically the one probably in terms of the cosine. Right, seen above. To evaluate that remaining polynomial. The terms of that polynomial. Let's look at a case. What if we had sine squared x times cosine squared x? Consider this integral. What about the integral of the sine squared x times the cosine squared x? Well, we do have our half angle formulas. The sine squared x, using the half angle formula, is 1 minus cosine of 2x divided by 2. And from the half angle formulas, the cosine squared x is equivalent to 1 plus the cosine of 2x divided by 2. Where this integrand can be simplified, the 1/2 times, well, the 2 in the denominator here can be multiplied by the 2 in the denominator here and factored out of that integrand as 1/4 in value. You will be left with this numerator times this numerator, which you'll notice is an a minus b times an a plus b form. So its result would be a squared minus b squared in value. And that produces a new integrand of 1 minus cosine squared of 2x dx. Where that integrand, to approach it, I'm going to have to now take this second power of the cosine and apply the half angle identity again. Which would say that's equivalent to 1 plus the cosine of 4x divided by 2 in value. Where now the integral will distribute, or 1/4 the integral will distribute across these two values in our difference found in the integrand, and produce 1/4 the integral of 1 dx for this first term, minus 1/8 the integral of 1 plus the cosine of 4x dx. The 2 in the denominator combining with the 1/4 to become 1/8, the minus coming from this sine scene here. And then we're just going to integrate this numerator 1 plus cosine of 4x. All right. So this will become x. This will become 1/4 sine 4x, and then when multiplied by negative 1/8 becomes negative 1/8x minus 1/32 the sine of 4x. added to 1/4 the integral of 1 dx, which is 1/4 x, we obtain these two like terms that can be combined to give me 1/8 x minus 1/32 sine of 4x plus c in value. That is what we're being told to do up in step number, in strategy 3, given up above. All right. Apply your, or I should say, rewrite your powers of sine and cosine using your half-angle identities. This will simplify to produce this polynomial of the cosine of 2x. That's what we got right there. Apply your integral rules for sine and cosine to the terms of this polynomial. Now, here at 1, when it applies, it's just going to be, right, lead to the value of 1/4 x, seen down below here. But in order to apply here, we repeat strategy 3. And use a more half-angle identity. Distribute that 1/4 of the integral, and we end up with our result. That is what is being summarized in this third strategy. Use half-angle formulas to rewrite into a polynomial of the cosine 2x. That was the 1 minus cosine squared 2x that we had. And apply the previous strategies to the terms of this polynomial forming involving the cosine of 2x. And when I say previous strategies, I should say all these strategies. Apply the known strategies, maybe we should say, to the terms of this polynomial form involving the cosine of 2x. All right. Those are our 3 strategies for the case of a product of a sine with the cosine function. Now you're going to go, well, what if my sine and cosine function don't fit any of these values of descriptions for m and n in statements 1, 2, or 3 here? Well, then consider rewriting them into statements involving tangent and secant, or cotangent and cosecant. All right? What you might see is if those don't rewrite into those other forms, where we're going to see some other strategies that could apply. All right? Let me pause this for a moment and let you take in this strategy list if you need to write this down. All right, folks. So if it does not fit one of these conditions for m and n for a sine of m of x times the cosine of n of x, then you might consider rewriting it, if it's a sine over a cosine case, into a case of tangent times secant, or a tangent times a secant, or if it's a case of a cosine over a sine situation, you might consider writing it into the case of a cotangent times a cosecant, where we do follow with those strategies. I see one little error in there. We need, how'd that x? Get that x back in there. That is what we see defined down below here. Tangent and secant functions. All right. What we're looking at here is the tangent of m of x times the secant of n of x dx. And I will say as we go through these that there is an analogous case for the cotangent cosecant pairing, right? The relationships between tangent and secants that we're familiar with, right? The integral derivative relationships between tangent and secants that we're familiar with are analogous for the cases of cotangent and cosecant. And we see that also in the cases here for the integrals for a tangent to the nth power of x times the secant to the nth power of x. There is a very analogous situation. All right. If we consider the situation of the tangent raised to the nth power of x times the secant raised to the nth power of x, right? If n is even and positive, and m is real, in this case we isolate a secant squared of x factor. We rewrite the remaining even factors of the secant in terms of tangent using this Pythagorean identity, and apply u substitution, letting u equal tangent of x. This does have the implication that du would be equal to the secant squared of x dx. And that secant squared of x that we will be using down here in our substitution will come from this one that we isolate, just as we had seen back in the sine and cosine strategies. This is now for an even power here on the secant. Pull out two of those evens. Rewrite the remaining as tangent using this identity and substitute in u for that tangent. Du then will replace that secant squared dx that you isolated and the differential dx that would be given in our integration, and allow for our substitution. All right. Now that's if n is even, the power of the secant is even, and m is real. If m is odd and positive, n is real, we fall into the case of case 2 here in our strategy. Here it tells us to isolate a secant tangent x as a factor. Rewrite then the remaining even power of tangent, because if you isolate a secant tangent, you'll pull one of the tangents out of the odd, leaving an even, and you'd be able to rewrite the remaining even power tangent of x in terms of secant of x using this Pythagorean identity, right? The comparable to the one we've seen up above. And then apply some u substitution, letting u equal the secant of x. Letting u equal the secant of x does imply that du would be equal to the secant of x tangent of x dx. And that's why we isolate this secant of x tangent of x initially. All right. That's the secant of x tangent of x that's going to replace itself along with this dx down here with the value of du. All right. Now, that's if m is odd and n is real. If the power on the tangent is odd and the power on the secant is real. Now, if m is even and positive and n is odd and positive, we don't have this condition for m, but n is odd and positive. Right? We don't have this condition for n either. Right? But they are opposite in their conditions. M is even, n is odd. Tangent is even, secant is odd. We rewrite the even power of tangent in terms of secant, using again the tangent squared of x equal to the secant squared of x minus 1. And this produces a polynomial form involving the secant of x, where you can then apply what are known as reduction formulas to evaluate these integrals, right? Where the terms of this polynomial can be evaluated using a reduction formula. Now, that's the other thing presented in this section. That's down below here. These are our reduction formulas. These are just for nth powers of sine, cosine, tangent, and secant, and there are analogous cases for cotangent and cosecant. Right? Where we would be applying in strategy 3 up here this fourth reduction formula. All right. Take note of these formulas. Let's look at an example. Let's consider the tangent cubed of x times the secant squared of x. That's a tangent times a secant. The power of m is 3. That is odd. And n is real. This is going to be strategy 2 we're going to apply. We're going to isolate a secant tangent of x. We're going to rewrite the remaining even power of tangent in terms of secant using that Pythagorean identity. And then apply a little u substitution, letting u equal secant of x. That will allow me to replace the secant of x, tangent of x dx with the value of du in my substitution. All right. If we go down below and we see that, right? I might point out here, note, since m equals 3 and is odd, really I should say an odd value, and n equals 2 is real, right? The tangent cubed of x times the secant squared of x dx can be approached this way. We're going to isolate a tangent secant, or a secant tangent, however we want to look at that. It doesn't matter what order we multiply that in. We're going to isolate a tangent and a secant. That's going to leave us an even power of tangent that I can rewrite using this Pythagorean identity. Now, rewritten, I can go into the secant of x's and let u equal those secant of x's. That will imply du dx equals the secant of x tangent of x, or that du is just equal to secant of x tangent of x dx. Implying that in my integral, which we have seen written this way, the tangent of x, secant of x dx will just become the du. The secant of x squared here will become this u squared minus 1 times this secant of x, well, that will become u. Where that u does distribute and becomes u cubed minus u as an integrand, which does have the ni derivative 1u to the 4th minus 1/2 u squared plus c in value. Where we don't want to leave that answer in terms of u, where since we might say u is equal to the secant of x, we can express our solution seen here. The integral for the tangent cubed of x, secant squared of x dx is equal to this result seen above, where we replace in for u the secant of x. 1/4 secant to the 4th power of x minus 1/2 secant squared of x plus c in value. All right. So that is just looking at strategy 2 up above. But again, these are very analogous in their strategy to what we saw for sine and cosine cases. And there is a very analogous strategy for the case of cotangent and cosecant cases. We're not actually going to present that strategy. We're going to rely on what we've stated here for tangent and secant and allow you to develop the case for cotangent and cosecant. But I do want to show some reduction formula in play. So here's secant to the 4th power of x dx. Here I can use a little reduction formula. All right. This is reduction formula for the case of n equal to 4. All right. And if we go up to that formula for the case of n equal to 4, it is 1 over 4 minus 1, the secant of 4 minus 2x, tangent of x, plus 4 minus 2 over 4 minus 1, secant raised to the power of 4 minus 2 of x dx. Plugging in 4 here makes 1/3. Plugging in 4 here makes the secant squared of x. So we have 1/3 secant squared of x tangent of x develop here. And that, notice that in our result. 1/3 secant squared of x tangent of x to begin with appears here. Plus, now this is n minus 2 over n minus 1. n minus 2, 4 minus 2 is 2. 4 minus 1 is 3. So it's 2/3. The integral for the secant squared of x dx. And what do we know about the integral of secant squared? Is it's simply tangent from our fundamental rules. So in the end here, we end up with 1/3 secant squared x tangent of x plus 2/3 tangent of x plus c in value. And those, folks, are our trig integration strategies for when we're facing things that are the powers, or I should say the products of tangents and secants. Here's this just a product of a bunch of secants. Right? We could have a product of a bunch of tangents, cotangents with cosecants, or sines with cosines. In the case for sines and cosines, we have these strategies seen early on in the notes. For the cases of tangent and cosecant, tangent and secant, we have these strategies presented here second in the notes. I don't present the cases for cotangent and cosecant as they are very much analogous to this situation here. Right? Instead of secant of n of x, where n is even, you would have cosecant of n of x, where n is even. And you would still isolate a cosecant squared. And you would rewrite the remaining even factors of the cosecant in terms of cotangent, using their respective Pythagorean identity. And then you would apply some u substitution, letting u equal the tangent of x, where du would then be equal to, I believe it is it opposite? Du would be equal to cosecant squared of x dx. I'd have to look that up. Yeah, cosecant squared produces opposite. Careful. Or cotangent. Where's cotangent? Yeah, looking at the integral rules, number 1. Yeah, cotangent produces opposite cosecant squared. So it would be opposite du would be equal to the cosecant squared of x dx. You would have a little opposite in this calculation. And I believe that would carry on down to here. Also, yes, it would. It would carry on to this example. Right. What we don't have is an analogous formula seen here. You could always develop that, folks. I do believe the book has some development on that. Or you could always Google that too, and you could certainly find that if necessary, if you needed that reduction formula for a cosecant to the nth power of x. Right? But the cotangent and cosecant case would be very analogous to these strategies seen here. All right. With that said, folks, we're at a little over the 30-minute mark, so I will go ahead and end there. I hope you're doing well. I hope you're watching these videos, and I hope you're finding them useful. I'll be back in class to work through some more examples, and I'll see you all next time.